Okay, let's start. This is Computer Networks, Lecture 2. Seems like most of you came back, so that's a good sign. A few announcements to get started. There are several homework 0 missing. It's absolutely necessary that if you want to continue, you have to submit homework 0. So there are 9 homework 0 missing. Some of you actually emailed me the files. That's fine because some of you are not set up on the Blackboard yet. But now everyone should be on Blackboard, so just go online and check if your homework 0 is submitted. Please do that today, immediately after the class. Homework 1 is due this week. Hopefully you guys are working on it. It seems like some of you are, based on the questions that we saw on the discussion board, so that's good. Keep most of your discussions on the discussion board because other students benefit from it. And that's one of the things that you have to learn, to ask for help and to provide help. Homework 2 is already released, and it's due next week. It's going to be a little bit more work than homework 1. So if you're done with homework 1, you should just get started with homework 2. There is no point in waiting. And homework 3 will be released today, and that'll be due the week after. Again, the reason I'm releasing all these homeworks early is everyone has different schedules, so you get a chance to work at your own pace. There's one other reason why I'm releasing all these assignments early, and that is to give you a chance to reassess. If you're still not sure if you want to take this class or not, if you have some other programming-oriented course that is also requiring a lot of work, this will give you a real taste for what you've signed up for, which is a lot of programming. And I actually warned you even on the first day, right? So just take a look at homework 1, homework 2, as well as homework 3 that will be released today, and hopefully that's enough data for you to make an informed decision about if you want to continue in this course. So a few comments about homework 0. So let's read this. You should submit a single file, the source code. So obviously some of you did not pay attention to this. I got multiple files in the zip file, so that is not what I asked for. No need to submit the binary. There are a bunch of other files. You're just supposed to submit the single source file. Please submit your source code through Blackboard. Again, some of you emailed me because you're not set up, but some others actually emailed me just because maybe you wanted to be sure I got them. Please don't do that. Just submit everything through Blackboard and we'll get it. It's a pretty reliable system. Please include a few lines of comments at the top of your file describing how to compile your file and if there is anything unusual about your implementation. Some of you actually started putting README and extra file, extra descriptions. So for example, if you put extra description on Blackboard, so there's a little text box where you can put notes, right? We don't read those. When we say put your explanations, if there's something unusual in the source code, you can't be more precise than that, right? So please follow the instructions carefully. I don't want to be too harsh here. I sometimes forget, make mistakes following instructions, but if you could just read the submission instruction next time before you submit the homework, and if you just spend an extra minute there, just making sure all of the instructions are followed, I think that'll help everyone. Because when you're looking for a specific item in your assignment, we know exactly where to go and look for it. For example, if you submit it in a different way, it's hard for us to know where it is. Some other observations. Some of you actually made assumptions about how big the input can be. For example, there was one submission that declared an array of size 20, and of course it worked in the given test files. But what's the problem with that? Can someone tell me?
Can't resize it if it grows too big on larger input, basically.
Yeah, you're going to get a seg fault, right? So, for example, if one of the inputs files has more than 20 lines, and if you're reading that into an array of size 20, it's just not going to work. You don't have enough memory allocated for this particular task. Some of you made some assumptions about where the input file has to be or what they have to be named. Again, I should not have to make those assumptions, right? You just specify the full path if you want on the command line, and you just read that. Yeah, so file names were different sometimes. Please pay attention to the submission instruction. Again, I think there are a lot of you in this class, and if you just spend an extra minute before you submit the homework, that'll help a lot. And also, that'll ensure that we spend our time being careful about your actual submission rather than hunting for okay, this particular part, where is it, right? So that's clearly not a good use of our time. So let's spend a few minutes reviewing and slightly adding to what we talked about last time. We talked about various network performance metrics last time, right? And here is another way to visualize what's going on when we have a network protocol. So we'll actually see these type of diagrams quite a lot in this course, and this is a chance for us to develop skills to interpret these diagrams. So you'll see these two vertical lines with typically arrows pointed down. So that's the direction of time. And these two vertical lines, they represent two nodes that are communicating. Does that make sense? So there is a node 1.
Excuse me.
Yep.
Excuse me. I need keys.
Yeah, go ahead.
Somebody come. Thank you.
So here is node 1. So that vertical line tells us, okay, there is node 1. It's sending and receiving certain type of messages. We will think about that. And here is node 2. So that's the second vertical line. So as we said, time is pointing down. What that means is if you want to know what happened at time t1, and let's say that's the beginning of time, then you go to the top part of the figure. And if you want to know what happens after t1, you start moving down the line. So what's the first thing that happens in this particular communication protocol? So node 1 actually sends a request. We don't know what it is, but it sends something called request to node 2. Does that make sense? And why is that line slanted down, that request? Yeah, so it takes time, right? So you send a message at time t0, and the message is not going to be received instantly at node 2. So there's going to be some delay, and that's the reason it's slanted down. So that first part of the delay is called propagation delay. And it's the physical time it takes for a message to propagate from one node to the other node, if you're sending a message from node 1 to node 2. And this is related to the speed of light, usually. Okay? Now, in this particular communication protocol, we're thinking of a scenario in which node 2 receives a message, a request, and it has to do some processing to compute the output or the reply. So that delay is typically called processing delay, because node 2 is going to receive the request at t1, and it's going to do some processing. Processing could be, for example, reading from a file, right? Processing could be computing some numerical value. Processing could be maybe fetching the information from yet another network service, for example. So processing could be anything that the node has to do to compute the request. So that's called processing delay. So what's the processing delay in this scenario? Can you just tell me what's the length of processing delay? You should be able to give me that answer based on the annotations that are on the slide. T2 minus T1, that's right. At time T2, node 2 is ready to reply, right? Now, there is another type of delay that we've labeled there. It's called transmission delay. And what that has to do with is the fact that you have a certain amount of information that you need to reply, but you can't transmit all of that instantly. It takes some time, right? Even if you compute it, and even if you know, okay, this is what I'm going to send back, it takes time. For example, if you download a movie, you know exactly what you're going to download, but it takes time, right, to transmit that information. It has to do with the capacity of the channel. right? So let's say we have a channel that's 128 kilobits per second. How long does it take to transmit 128 kilobits? 1 second, right? So that's the transmission delay. It has to do with the capacity of the channel. In this scenario, it's T3 minus T2. And finally, the reply is received at node 1. Starting at time T4, the complete reply is received at time T5. So what's the round trip time here? Round trip time is another phrase that we'll use a lot. It's basically how long it takes for a message to go to the intended node and for the reply to come back. What's the time between sending a request and receiving a reply? So that's called round trip time. All right, so here's so now just directly relating what we talked about to what we covered in the last lecture. We talked about bandwidth and delay. For instead of bandwidth, we use the word throughput, if you remember. For now, we can think of them as the same. They are slightly different, but let's think of them as the same. If we have a communication protocol that only sends a small reply, small response in response to a request, what is more important? Delay or bandwidth? Delay, right? Because the round trip time is going to be dominated by how long it takes for the message to go from node 1 to node 2 and how long it takes for the message to come back. But what if the response is of substantial size, for example, a movie file? Does delay matter? Probably not, right? Because the time it takes for you to receive the complete response is going to be dominated by the capacity of the channel. Does that make sense? So that's exactly what we've written down there. So the other topic that we covered in the last lecture is the idea of protocol stack and encapsulation. And just to recap very briefly, when we're talking about network protocols, we think of them as a series of protocols providing different levels of functionality. So let's look at the network layer. Everyone can see the network layer, right? For example, here. So network layer uses services provided by the link layer. And later in the course, we will learn about what those services are. And it provides services to the transport layer. That's how it works. You use services provided by the layer underneath you, and you provide services to the protocols that are above you. And what is protocol encapsulation? Is the idea that when you have these services that are provided by a series of protocols, because we're using the whole stack, when one layer composes a message and sends it using the services provided by the layer underneath, that layer underneath has to include its own set of information for the protocol to actually work. So what's happening is the message that was sent by the layer above is encapsulated in the message that is sent by the lower below. So that's the idea. So let me just zoom through that. So any questions on what we've covered so far? So this is pretty much what we did last lecture. We sort of had to rush through the very last part, so I thought I would just spend a few minutes talking about them. No, okay, good. All right, so what we're going to do is, again, this might be too elementary for some of you, again, based on what I've seen in the discussion board. But I think some of you are still struggling a little bit using Linux. Not too sure exactly what you're supposed to do and stuff like that. So I'm just going to go through a few steps here, on on the lecture so that it'll be clear to those of you who have never done this kind of stuff before. Okay. So as we said, we will compile and test your homeworks on Bayou. I think everyone has an account on Bayou by now. Who does not have an account? Is there anyone who did not get an email from me a few days ago? Okay. So can you email me with your email ID so that we can create an account for you? Just two of you? Everybody else has an account? Okay. All right. So let's assume everyone has an account. Now the question is, what do you do with it? There are two ways in which you can use this system. If you want to do your development on your local machine, again, this is going to be a repeat of what has already been discussed on the discussion board, right? So you can install Ubuntu on your machine and do all of your development there. And when it's time to test it, because we're going to eventually test your programs on Bayou, you have to copy those files on this machine called Bayou, right? The way to do that is by using a program called SCP if you're using Ubuntu. If you're using Windows, you might use a program called WinSCP, for example. If you're using Mac, you can use SCP from command line. I'll just show you how it works. Let's see. So here's my terminal. Let's see what files I have. So let's say I want to copy the file called, let's see. Let's say I want to copy that file called iperf. So let's say this is my text file that has the program, right? So I'm on Mac, so I can just use SCP. So that's my email ID. And I can just put that or whatever target directory I want. And the file, it claims it got copied, so we're going to actually look at it. So this is how you transfer files. So if you want to transfer a file from Bayou back to your local machine, for example, you can do something like, so now we know that there is a file called iperf on Bayou, right? Because we've copied it. We can just give it a local name, perf test. So I copied the file back to my local machine. If you're using Windows, you're going to use a program called WinSCP. It has a nice graphical interface. It'll be even a lot easier. It'll be basically you'll have one part of the window that'll open the remote machine. One part of the window will be your local machine, and you can just drag files back and forth. A lot easier. Even on Mac, you can actually get software that provides that kind of graphical interface. So that's the first part. How do you copy files back and forth? And the reason you want to copy files to Bayou is you better test your homework on Bayou because that's where we're going to try to compile and execute your programs. Okay? Now the second part is how do you actually, let's say you've copied your files to Bayou, and how do you actually log in there and compile your programs, right? So that's the second part. So for that, again, depending on what platform you're using, you're going to use a different command or different program. So here I'm going to use something called SSH. So that's my user ID, and that's my user ID at hostname. All right. So it says I'm logged in. You can see it here, my user ID. And that's the host name. So one of the commands that I can use now is called ls, basically lists what's in there. And it turns out this file called iperf is in there. Did you guys see that? We just copied that, right? Now, if you want to do some quick editing, you can use something called Emacs, for example. I can type whatever I want. It's just a text editor. Again, if you're not familiar with working in this kind of environment, it's probably more productive for you to copy files back and forth rather than using this. For me, I'm very comfortable using the terminal type environment. So for me, editing the programs and bio is not a problem. I think it's worth learning how to do it, but if you don't have time right now, you can copy files back and forth. So let's say, let's actually write a program. So we're just going to do hello world. So this is just a text editor, right? This is just a text editor. I could have just used Notepad or whatever else you might have on your local system and copied it over there. So let me just save this. Now if I do ls again, I see a file there called test.c. I can look at the content of it. So there's another command called cat. It stands for catenate. So it shows the content of that file, right? So now how do I compile it? We've asked you to actually do a make file, right? So you actually have to do it here, but we're not going to do all that here in this quick demo. But I can use this compiler called GCC. Let me actually introduce some errors there. So there'll definitely be an error, right? So there's an error on line 4. GCC is the compiler. GNU CCC. So there's a that was a syntax error, right? So I save it now. So let's try GCC again. Oh, no complaint. There is one thing that you might want to do. You can actually specify what the output should be. For example, in homeworks, we've specified the name of the binary, right? For example, I forgot the names. It's I think it's a client chat and servers chat, something like that. Chat client, chat server. Yeah, that's right. We're just gonna say test hello. I'm just saying the output should be called test hello. Now, if I do an ls, you can see that there is a file called test hello now. So that's the binary output. And the way I execute that is by just typing that, and it said hello world. So that's how I edit files if I need to on Bayou, and I compile it and I executed that. Any questions on the general workflow for the homeworks? Again, this is going to be pretty familiar to at least some of you. I don't know how many. But I think it seems like it's kind of new for at least some of us in this room. So I thought it's worthwhile just showing you the workflow. All right. Any question? Yeah.
Do we have to use C or can we use C++?
You have to use C. Yeah, you have to use C. For homework 0, you could use C or C++ because they were designed to just make sure you know how to program. But from now on, we're going to use C unless otherwise specified. Because some of the assignments later might use some kind of bash scripting and things like that. Okay. All right. So that's how we're gonna do our homeworks. We can edit things locally. If we do that, we're gonna copy files back and forth. Depending on the platform, we're gonna use different programs like SCP, WinSCP, etc. And when we need to compile and execute programs, we're gonna SSH into the machine, and we're gonna use this. If you are using Windows, there is, I think, there are a couple programs that you can download for free, and that allows you to SSH. One is called Putty, P-U-T-T-Y, and there's another one called WinSSH, maybe, I forgot the name. But you can find these online, just search for it. And if you can't find it, post questions, and I think someone will help you. All right, and when I'm done with everything, I can just exit or log out. All right, done with that. Cool. So that's what the slide says. So now, once you've seen the demo, it's pretty straightforward, right? Just wanted to spend maybe a minute talking about why are we doing this? Why not use Windows? It's a really nice visual interface, etc. That's true. Microsoft actually produces excellent integrated development environments. Everyone knows that, and that's why everyone likes using them. But if you look at how most of the infrastructure in the internet is built, it's not built on Microsoft Windows. So if you want to really learn how networking works, it's actually worth spending a little bit of time learning how to use Linux and learning how to program in C. And that's the reason we're doing this. It's not just to make it a lot of pain for you guys. It's not that. If you, for example, just want to do iPhone programming or Android programming, you probably will not use a lot of C. But if you end up going and working for an internet infrastructure company, you will most likely work on Linux or Linux type environments, and also you will have to be very familiar with C or C++ increasingly these days. All right. Okay, so let's talk about network applications, because that's what we're gonna spend a lot of time thinking about in this lecture. So here are the two most common architecture that we use when we develop networked applications. So first of all, you guys are already familiar with some of this terminology, I think, but we're going to look at it from a slightly different perspective. So first one is client-server. So there are a bunch of clients and there are a bunch of servers. You guys have heard of this terminology before, right? And the point of network applications is you have applications running on different nodes, and they need to communicate with each other, to exchange data, to ask questions, to receive answers, etc. Right? So in this architecture, it's obvious how client might request for some information to the server, right? Okay, I want the content of this file, for example, and how the server might respond to that, saying, okay, here's the file, here's the image file. But how can we get two clients to talk to each other in this architecture? It's a client-server architecture, but still, if it's a network applications, many of the network applications will involve two clients talking to each other. I'll give you an example. For example, Facebook, right? It looks like a client-server type architecture. You're a client, and there's a Facebook server or a collection of them, and you are interacting with Facebook, right? But eventually, you'll have to communicate with your friend, who is not Facebook, who is not a server. Your friend is another client. So how do we actually get that to work? Communication between the clients. The server is going to be the intermediary to make this communication happen, right? So for example, if client 1 needs to send a message to client 2, client 1 is going to tell the server, okay, here's a message, please deliver it to client 2, and the server is going to send that message to client 2. Does that make sense? So client-server does not necessarily mean, okay, just client talking to a server. But there's a little bit beyond that, which is a server is going to provide the intermediate buffering and communication and coordination so that communication between the clients can happen. Let's think about a different architecture. It's called peer-to-peer architecture. In this architecture, all the nodes are equal, in a sense. There's no server. There is no server coordinating the communication. If you need to send a message to some other node, you directly connect to that node and send a message. And if that other node needs to send a message to you, that node will also directly connect to you and send a message. So that's the peer-to-peer architecture. Can you think of an example of what's an example of a peer-to-peer system? BitTorrent. Okay.
TCP/IP.
Why do you say it's a peer-to-peer?
Well, you don't actually connect to a server, you connect to each other.
Yeah, that's right. That's a very good example. I wouldn't say it's a application, but it's a very good example of a peer-to-peer, this idea of peer-to-peer connection. So when you, for example, have When you have one node that wants to communicate to another node using TCP, you directly connect to that. Does that make sense? Again, I think a lot of this will be clear, once you actually work on homework 1. Okay. With a small caveat, there are actually various TCP/IP systems where you actually have an intermediary that is doing some coordination. One of these architectures we will revisit in the course later on. They're called NAT boxes. Basically, these are the routers, wireless routers that you have in your home. It turns out they have to tweak the messages and coordinate in various ways the communication between the external services and, let's say, you're using a laptop or a phone using that Wi-Fi. But for the most part, you're right. When you want to connect and send a message to another TCP/IP host, you just directly connect there. And there are actually a lot of systems that are hybrid of these two architectures. One example is Napster. Who's heard of Napster? It's a pretty old system at this point, but you guys have heard of it a little bit. They're still making a little bit of noise, not as loud as they used to. That particular application uses a hybrid architecture in the following way. In Napster, you go to their site or application, you can actually search for the songs that you wanted to download. That directory is centralized. So basically that Napster server has a list of all the songs that everyone has ever shared or wanted to share. But when you click on the link, you download not from the Napster server, but directly from the person who's sharing it. Does that make sense? So the directory is centralized. But when it comes time to actually download the file, you actually need to connect to the host actually that has that server. How about search engines? Or the way we search, I think that's a better way to phrase it. It's also, there is some centralized component there, right? For example, I go to Google, type something, that information comes out from Google servers, right? But what happens when I click on the link? It goes to the server that actually hosts the page, right? So this is also using both peer-to-peer and client-server type communication. Regardless of the architecture, we need a way for a node to send a message to other node across the internet. That's what we are talking about, right? And it turns out these applications, they are processes running on various machines. If you remember processes from your operating system course, for example. But if you haven't, just think of them as applications or computer programs running on a computer, a laptop or a server. So we need a way for one application to send a message to another application across the internet. That seems like the basic capability we need, right? But for that to actually happen, we need a little bit of infrastructure to facilitate that. First is called naming. Basically, we need to be able to say which node we want to send a message to. We need to be able to name the node. Just like if I want to talk to someone, I need to say, hey, so-and-so, do this or don't do this, right? Similarly, when you want to communicate with some other node, we need to be able to say, okay, I want to communicate with exactly this node. So that's called naming a node. Name could be numbers. A lot of times they are. But it's something unique that identifies that machine. But there are different layers to naming, it turns out, depending on the level of abstraction, depending on what you're trying to address. For example, let's say I want to send a message to my friend who is using a laptop, let's say from my laptop. One layer in this naming story is I want to send a message to that laptop, right? You guys have probably heard of IP address. Okay, IP address is A.B.C.D, right? But if you think about it a little bit more, it turns out that's not the complete story, because that laptop actually has tons of things running in it. my friend obviously didn't want this message to pop up and cover the entire screen, right? So this message actually needs to go to a particular application on that laptop. So that's also naming. We need to be able to identify exactly this application in that laptop. So we use the word naming broadly. It's not just laptop, or because depending on exactly what you're trying to do, there's going to be various layers of naming involved. We're going to get to that in a little bit later in this lecture. There's another piece of infrastructure called routing. You guys probably heard of routers at least. But routing is a little bit different from the wireless routers that we see at homes. That's almost a misuse of the terminology. Routing is basically an algorithm that tells us what paths to take across the internet to reach the destination of the message. Just think of it as a road network. Routing tells you which roads to take to get to your home, for example. Similarly, internet has basically you are connected to various ISPs and sites, and there are lots of links going out from UH, right? Which links are you supposed to take to get to the destination? So the routing algorithm tells you, okay, among all these 5 different links, I have to use this particular link to get to the intended destination. So that process is called routing. This is a little bit different from the wireless routers at home. Now you realize that, right? And the other piece is transport. Obviously, when we send a message, we usually want that message to be delivered reliably, for example, right? So some of that functionality is called transport, the exact definition and so forth. We'll actually cover that maybe 2 or 3 lectures from now. So those are the 3 major pieces. Again, this is not the complete story, but just wanted to give you a high-level idea. And you guys have heard of TCP and UDP, probably. So those are the transport protocols that are used very commonly. And you guys have heard of IP, right? TCP and UDP are transport protocols on top of the network protocol called IP. Okay? So this is how, roughly, you send a message from one node to another. You have these 3 pieces of infrastructure in place. How do you identify who or what you want to talk to? How do you actually get there among all the various paths? Because if you just take a random path, you're never going to get there. You need to know which paths to take in the network, and you need a way to send these messages reliably. Once you have that, there's a hope that we might be able to communicate with the intended machine. And let's talk about application protocols. So we all know what network applications are, right? Network application is not TCP/IP, for example. Network applications are what we install on our phones or browsers, email clients, applications of that sort that need to send messages to the network and receive messages from the network for them to function, to do their work. So those are network applications. These applications use TCP or UDP to send these messages. And because these are network protocols, there has to be an agreement between the sending process or application and the receiving process. There has to be some kind of agreement. Otherwise, the receiver will not be able to understand what the sender actually meant, right? So let's think about how we write network applications. So now we sort of understand how it works, if you think about the system. But that is not how we typically write network applications. So if you're familiar with, some of you have probably developed some Facebook applications. Who has developed some Facebook-based applications? Anyone here? Yeah, you have. Okay, you have too. So you're familiar with Graph API, right? So what is Graph API? It's basically a way to collect information about a user, right? For example, if I want to write a Facebook application, where let's say you enter your Facebook ID and password, and let's say we want this application to pull up all of your friends, right? So that's a network application, right? Your application needs to go to Facebook and then grab all of your friends and maybe present it in a way that's useful to you. For example, let's say you want to sort all of your friends by the state they are in right now. I mean, the default Facebook application does not allow you to do that, so you have to write your own application to do that, right? So what you do is, so Facebook API basically provides these function calls. And when you're writing an application, you just call these functions. For example, you just say you want to grab all the posts on that particular page. Then that's the function you call, and then you get a call back, and okay, here are all the posts, right? You want to grab list of all the friends of the logged in user. You just call that function, and that's it, and you get the list of your friends. Then the question is, how is everything that we talked about until a minute ago, how is that relevant? It seems like this is how real networked applications are written right now. This is the networked application, right? How is that relevant? So we're gonna answer that question. But before that, let's think of something even simpler. Something simpler. Let's say we want to write a network applications that provides timing service. Because we know all of our clocks can be off by a little bit. So instead of doing that, to solve this problem, let's have a server that keeps the official time, okay? And we're going to have laptops or phones or whatever, get actually that time from the server. That's how cell phones sort of work, right? Otherwise, I would have wildly different times on different cell phones. So let's think about the messages that need to be exchanged between the laptop and the server if you wanted to write this network application. So what does the laptop need to send to the server? Request. Okay, what's the current time, right? That's the request we want to send, right? And how about the server? So how should it respond?
Here's the time.
Here's the time. Yeah, exactly. It's 2 o'clock or whatever. So we need to send some type of message to the server, and the server needs to send some type of message back to the client. And is this a client server or a peer-to-peer architecture? It's probably client-to-client, client server, right? And here's what the protocol timing diagram for that particular application might look like. So what's the time? That's the first message that goes out. There is some propagation delay. The server receives it. Server is going to do some processing. The processing in this case, what's the processing delay in this case? We said the server is hosted in an atomic clock facility. It probably needs to go look up what the current time is, right? That's the processing delay, and the server is going to send a response back to the client. Okay, it's 2 o'clock. So that's the protocol diagram. We designed the protocol, and we've analyzed, what are all the possible sources of delay. And it's actually very important to analyze this kind of protocol. So what's the problem with this protocol that we just designed? Think from an application perspective. What's the goal?
The time.
Get the time. Does it work? I claim it's broken.
It depends on whether or not they're calculating and processing the time, whether or not they're calculating what time it's going to be when it gets back to you.
Yeah, but that's kind of hard, right? But I have no idea because there could be retransmissions, this path could suddenly be longer. It's kind of hard. So this protocol might actually be broken from an application perspective. Does that make sense to everyone? Yeah. Okay, good. Let's think of a different application. Let's say we want to design a cloud-based file backup application. Everyone's heard of the phrase cloud, right? Cloud computing, etc. But for now, let's just think of it as we're just using a server. We don't care where it is. It's somewhere out there in the internet. So we want to design an application that we run on this laptop, and click a button, and it'll just back up all of the files. That's the application we want to build. So we want to run this application on the laptop. But there is a counterpart to that application, right? We also want, some part of the application to also run on the server, don't we? Otherwise, how is the server going to receive our files, right? So the applications run both on, my laptop, if that is, what I want to back up, and also the server. And who is going to run these applications? Maybe on the laptop, the user, on the server, maybe automatically when we design this server, and what messages are exchanged. That's the most important topic when we're designing network protocol. So can you suggest what are these messages that are exchanged? So what kind of messages would laptop send to the server for this application? Remember, our application is we want to be able to back up our files in the cloud. So what kind of messages does this laptop need to send to the server?
You want to check if there's the file there already.
Okay, so yeah, but let's say we start from scratch. So so maybe the first one is
Hey, I want to send you some data.
yeah, I want to send you some data, right? Maybe that's the first type of message. There's going to be multiple types of messages that the laptop needs to be able to send. So the first type is maybe, okay, here are all the files. That's the most basic one. If you want to make that better in the sense that maybe we don't want to use up all the network capacity if all the files are backed up. Maybe the second type of message that laptop needs to send is, okay, here are all the files I have. Here are the last times they were modified. Do you have all this? That's the message you might want to send to the server, right? What's the third type of message? Or is there any other additional messages that might be useful?
Well, maybe the server doesn't have any room for additional files.
Yeah, but I'm talking about the message from the laptop to the server.
Well, that's what I'm saying. You could ask if you have room.
Exactly. So, do you have room, right? Maybe another message would be, okay, I want to actually use this service. Am I authorized? Maybe this is a paid service, in which case one of the messages might be, okay, here's my username and password in some form. Give me a key to the storage service. And what are the messages that the server might want to send back to the laptop? Say that again.
Authorized to use.
You're authorized to use it. Yeah, depends on, first of all, which the reply obviously depends on the request, right? So if the request was, okay, here's my username and password, am I authorized to use your service? The reply might be, okay, you're authorized to use it. If the request was, oh, here are all the files, just store it in your hard drive, then the reply might be, okay, I was able to store everything, or I was not able to store everything, I ran out of space. So there was one other message type that we talked about. What is that? Do you already have this file, right? And what are the possible replies to that?
Yes.
Yes or no, right? Okay, so by thinking about how we might build these two applications, hopefully we have an idea now that in order to implement network applications, we're going to have to exchange a lot of messages back and forth between various nodes across the internet, if that is where we are running the applications. Now, where does this come in to this story? But again, we're not sending messages back and forth. We're just calling these functions. So what's going on?
Well, the API is taking care of all the little stuff for you.
Exactly. So what the library does is when you call this function, for example, it's going to compose that message and send it out. When the reply comes back, it's going to call one of these functions, and it's going to tell you, okay, here's a list of all of your friends. So this is where it comes in. So if you've used this kind of API already, some of you have, to do Facebook application or other types of applications. Now, hopefully, this gives you a little bit more understanding of what's actually happening underneath. So this particular library is taking care of sending the messages, receiving the messages for you. All right. So let's take a 2-minute break, and we'll actually talk about how we might send messages using TCP/IP. Some of these types of messages that we talked about. Okay. Just stretch, stand up, whatever.
That 2-minute break.
Yeah.
How do give example of peer-to-peer?
Example of peer-to-peer.
So what's the difference? Let's say you have a website, local or whatever,
Yeah.
and type it in Firefox. Go there, so this client server application, and I go to communicate on this.
Hey, Theo, have you been to the house yet? Oh man, you haven't. Okay, well, because we're wanting to, for the in the house, we were thinking about a light gray. I mean, we were thinking about instead of white, we were trying to do light gray. So,
Everything I need to do.
is it too late?
Questions, concerns? No? I have a question sort of specific to the homework. I don't think it's happening there. Okay. So I could remind us something else we said what? That's something just the way that I
Yeah.
also read that he's super slow. So is it going to be a problem?
Well, I think homework 2 is this HTTP client, 3 is going to get to the server, and homework 4 is going to that's limited for like inventory. For 2 and 3, we don't care. And as long as you can, for example, HTTP client, and one then one client, that's what I want.
Well, no, I implemented selected on my It would be tempting to use any of it. I was just wondering because I just heard that
What we could also do is, yeah, I think it's fine for now. I wouldn't worry about it. That you're doing one character at a time. You can repeat characters. Yeah, exactly. You're just a bit concerned about performance.
Well, I'm not even concerned about the performance of it. I mean, if that's okay with me, just
Yeah,
I love to learn this. I don't know if that's for this class.
Yeah, we're not going to do multiplayer. That's conceptually it's a little bit easier because you just read the source code and the operating system speaks here. Inventory is a little bit harder to understand and get used to because in multiplayer programming
I have to find someone. I know a few people that speak. Go public. Diego.
What's that?
Yeah,
Yeah, that's right. Yeah. All right. Let's get started. So the question is, how can we get applications to send a message back and forth? If you're using Facebook API, you just call those functions and that's it, right? But if you're trying to build this kind of networking services from scratch, we don't have that luxury. So we need to know how to use TCP/IP to send these messages between different nodes. What we're going to use is something called Sockets API, and this is what you're working on this week, right? Good. Higher level APIs build on them. For example, Facebook is going to, Facebook API is basically just calling functions, but the way that's implemented is by using sockets underneath. So Facebook API actually does that if you're using Facebook function. But if we wanted to build our own applications, we'll have to use socket programming ourselves, or socket API ourselves, and that's what we're going to do. After you've set up the sockets, and we're going to talk about how to set it up, they look just like files in Unix. And what that means is you guys already know how to do network programming. That's what it means. Because you guys already know how to read from a file, you guys already know how to write to a file, right? Because that was homework 0. So that means you guys are already, network programmers. That's kind of nice. So a lot of times we have a client and a server, node 1 and node 2, and we're thinking about how to get these applications to send messages to each other. A nice consequence of what I just said is if you want to test the protocol, you can have the client write to a file and server read from that file. You guys already know how to do that, right? Can you guys design a system where one program writes to a file and another program reads from that file? You guys already know how to do that, right? You could actually. This is a perfectly fine way to test network protocols. It turns out, because the sockets, once you set it up, because this is the mechanism that allows you to send messages from one node to another. They look just like files. So you're going to pretend these are files, and you're going to just write to this special file, and you're going to read from this special file. So sockets are these special files that allow you to send messages from one node to another, but we're going to interact with this special file just like any other file. Opening, reading, writing, closing. And this is probably your first computer science course, right? How to interact with files. So as we said, sockets are special files. These are not files on your file system that you create, let's say, when you're editing a program. They're a little bit special. And all that means is, you might create them in a special way, but once you've created them, the way you manipulate them, it's very similar to how you manipulate a file. So we're going to use something called system call to create these files. Because we still need to create this file that ties up these two applications, right? So we're going to use something called system call. And again, you've probably seen this in your operating systems course. If you've taken that, it's basically these are special instructions provided by your operating system that allows you to interact with certain type of resources only if you have the privilege to do so. For example, if you want to access some devices, if you don't have certain privilege, you might not be able to do that. And system calls actually control and gate this type of request. For example, applications will request I/O operations through system calls, because you might actually have various applications that are trying to write to the same hard disk, right? Because I have multiple applications running on my laptop, and they might all be trying to write stuff to the hard disk. There has to be something to coordinate this, right? Similarly, I might have multiple applications on my laptop trying to connect to the internet. There's only one network interface. There has to be some control and gating of this kind of request, and these are typically done through system calls. And there are higher level functions that are built using system call interface. For example, if I want to write stuff to the output called standard output, which is printf hello world, I didn't really do a lot of system calls, right? But I just used this function called printf. The reason that works is that the way printf is implemented is using system calls. So printf is going to call, ask the operating system, okay, I want to do this on this special device, can I do it? You didn't have to do that. You just said printf, right? But that's what's happening underneath. This is actually making a system call. So most input-output operation in Unix is done through file descriptors. For example, we've all done printf, hello world. That's what we did earlier, right? What's that F in printf? It's format, right? We want to format that output. And you've done F printf. What's the first F in file printf, right? Could you, for example, use F printf to do something that looks very similar to printf? It turns out you could, actually, because the standard output, which is the terminal, that's just another file. So if you know exactly which file it is, and if you write to that file, it will appear on your terminal. Does that make sense? And you guys have all used scanf probably, right? That's how you get input from the user. Have you used fscanf? What's fscanf? It's from a file, right? You read from a file. So it turns out if you know exactly which file it is, you can use fscanf and specify the file, and that's just like getting input from the user without using scanf. Usually we use fscanf only when we want to read from a physical file on the disk, right? But if you know exactly which file corresponds to users typing in the terminal, if you say I want to read from that file, you can actually use fscanf. All right. So there's this data structure called file descriptor. So basically, this is a data structure that keeps track of all the information necessary to interact with that file, and this structure is in the kernel. So whenever you need to read from a file or write to a file, you need to go to that data structure and identify, okay, exactly which file, where it is, is it a special device or not, etc., etc. So this is how you open a file, actually. And you can read more about file descriptor. So why are we talking about file descriptor? The reason we're talking about file descriptor and all these examples about fscanf, fprintf, etc. is when you open a socket, it just becomes a file, right? It's just a special file. So we're going to use that file descriptor to write to that file. And that's the reason we're talking about file descriptor. All right? And just like any other function calls, whenever you try to open a file, a regular or a special file, you get different type of error values. You need to pay attention to that. For example, if the file doesn't exist, then it's going to tell you, okay, it doesn't exist. Here's the error value, etc. Okay. So again, here are different ways in which you might interact with a file. You might manipulate a file, read. That FD is the file descriptor. It's just an integer. That's how you identify a file, it turns out. For example, what's the integer that represents the standard output? 0, that's right. So if you just say, I want to write, 0, and here's the buffer, here's the number of bytes. If you execute that, that message will actually appear on the terminal, because it's just another file. It's a special type of file. Right? And you can write to a file, you can seek. I'm not going to do this on sockets, but we're going to read and write from socket, because when we set up the socket, we're going to talk about that in a slide or two. We're going to read from that file, write to a file. So the question is, so it's just going to be exactly like how we read from a file, write to a file. So how do you actually create this file? That's the question, right? So that's called, how to, set up a socket. There are two types of sockets: unreliable and these are UDP sockets, and stream sockets. These are TCP. Again, the names might not be very important right now. We're going to talk about them in detail later in the course. One thing to keep in mind is when we're thinking about network applications, and let's say we are reading from a file. Again, this is reading from a file, right? When you read, you might not get the full message, and you might just get a partial message. And what that means is you have to read again. It's the same thing, right? If you have a huge file and you want to read the whole content, you have to read multiple times, right? Until you reach the end. In communication protocol, it's the same idea. All right? So these are the function calls that you might make to create the sockets to enable communication between the client and the server. So it turns out you call this function to make a socket. Again, it's a special type of file. I'll show you an exact example, and there are some readings on the schedule page as well, right, to really understand how all of it works. Create a file, this special file, and you need to say, okay, this special file called socket, this is going to connect, this application on this node and this other application on this other node, right? Part of that is done with bind. You're going to say, okay, I'm going to create this socket, and this is associated with this address, this application, this port. And you're going to connect to another application, another port, on a different machine, and that's how the communication is established. You can create this special file and say, okay, one end of this file is connected to my IP address, my application, my port, and The other end is going to be connected to this other machine across the internet, its IP address, port, etc. So once you've done that, you've established a connection. So in order for you to establish the connection, as we talked about earlier, you need to be able to name what the two ends of the communication are. And so as we said, there are multiple layers in naming. You need the IP address, you need to identify the machine. You need the port number. So this is just an identifier, just like you have all PeopleSoft ID, right? Similarly, when you set up a socket, you can just say, okay, I'm going to send a message that's going to have this ID. And when you want to receive a message, you can say, I'm willing to accept messages that have this particular ID. Think of it that way. These are called port numbers. Okay, so these are just identifiers. There are some well-known ports. For example, all of the HTTP messages, for example, the websites, it's done through port number 80. So if you receive a message with that says port number 80, then you know, okay, this is an HTTP message. That's the standard way of doing things. So these are called well-known services. What that means is just by looking at the port number, you know what application sent it. Yeah.
When you talk about ports, yeah, is it the same ports that you find in like a router or something? Like you can open ports in the router to enable certain addresses to come in.
Yeah, so you're talking about when you go to the configuration page of the router, you can say, okay, I want messages that are on this port to be able to come in.
Yeah.
Everybody else, it's the same port. Yeah. But now we already know the problem with this, right? This is a standard way of doing things, but there's nothing that's stopping me from sending messages that are not intended using that port number. Because this port number is something that is specified when you make all those system calls, when you create that file, right? So there is nothing that's preventing me from sending a completely different type of message, even using the well-known port. For example, I can send SSH over port 80. And your router will say, oh, this is an HTTP message, I'm going to let it come in. Even though your intention was to only allow port 80, the web traffic to come in, right? So you'll hear this phrase in a well-known port. What that means is there is a official table somewhere. For example, that location, if you're using Unix type system as well as Mac, if you open that file, you'll see that see a list of these well-known ports. So here are the 5 components that you need to establish communication between the nodes. You need the protocol, which protocol you're using, local IP address, local port, remote IP, and remote port. Here is we need when we set up a socket, we need to name the ends of the socket, right? And the way that is done is by putting information into this structure. For example, which family, IPv4 or v6. Which port number, which address, etc. So there's a structure. Just think of it this way. Again, the details, there's not enough time to go through the details, but the point is there is certain types of information that you need to specify to name the end of the socket. And you put all that information in this particular structure. There is one aspect of all of this that's very important when you're doing network communication, and you probably have heard of Indianness when you talked about architecture, computer architecture, organization. It's basically the way the bytes are organized in the network stream, right? For example, let's say I have a 2-byte number, right? I need to send from client to server. And different machines, they might have different, let's say, CPUs. They might have different architecture, right? And they might represent the same number in a different way. For example, in some machines, let's say I have a 2-byte number, let's say, in hex 1, 0, right? In some machines, you might represent them as 1, 0, and in some other machines as 0, 1. But when we communicate across the network, we cannot have this confusion, right? Let's say node 1 sends 1, 0. So how should the second node interpret that? Is that 1, 0 or is it 0, 1? There has to be a standard order that's agreed when you send this message across the network. And it's called network byte order or big endian order. And there are these functions that allow you to convert local representation into the standard network representation. For example, H stands for host, N stands for network. So basically this function will convert whatever you pass as an argument from the host order to the network order. Does that make sense? Because my laptop might represent 1, 0 as 0, 1, but if I call that function, then it's going to convert that to 1, 0. That's the network order. What if my laptop actually represents 1, 0 as 1, 0? What happens when I call that function? Yeah, it does nothing because it's already in network order. Does that make sense? So do you understand why you need these functions? Yeah. Right. And N to H stands for network to host. So when you receive a message across the network, you need to convert that to your local representation, local byte order, right? And you need to call that function so that you can do that appropriately. All right. So here's what a client looks like, a skeleton of a client. So let's say we're trying to build a client-server application. You have this structure. You want to have an IPv4 address, given port number, right? So you create a socket, and you specify the address type. You want to, this is the port number basically, and that's the IP address. Basically, you're just saying, okay, here's a socket, and we're gonna make sure that this end of this socket is assigned to this particular name. And name, as we discussed earlier, identifies one of the communicating entities here, right? So once you've associated one of the socket to this particular communicating entity, then you just say, connect in that particular case. And that actually establishes the connection. All right. Again, so that PDF that I linked from the schedule page, when it goes through the details of this, it's worth reading. And server also works the same way. A server is just a special program that instead of initiating a connection, it just tells the underlying system that I'm willing to accept messages that have this particular port number. That's all you need, right? So server makes a call to the underlying system, says, here I am. I'm willing to accept any messages that come in with port number, let's say 80. So the only thing that's special is you call this function called listen. You set up the socket just like before, but now you need to tell the underlying system, okay, here I am. Please send me all the messages that have port number 80. And what's that server that accepts messages on port 80? That's a web server, right? So that's how web servers work. You run this program, and this program tells the underlying system, operating system, kernel, that I want to receive all the messages that come in with port number 80. And when there is a message that comes in actually with port number 80, then you just accept that connection, and then you just read from that file. That's how web servers work. Here's a little helper function that makes it easier for you to set up the sockets. More information about that. And finally, once you've finished sending and receiving messages, you need to close the connection, right? There's a little bit of detail again, and I encourage you to go read on the PDF on the website. What do you do when you're reading from a file? Well, is there something special that you have to do when you're done reading all the content in the file? You have to close it, right? What happens if you don't close it? There could be conflicts later, right? And you're using up one of the file descriptors. Remember, whenever you open a file, the kernel has to keep track of this file, right? For example, what are the applications that are reading this file? What's the current read position? So on and so forth. What happens if you don't close a socket? Because socket is another special file. What happens if you don't close it? This connection stays, on your machine, right? And what's the problem? First of all, you're tying up resources. Does that make sense? Because this connection is there. Even though you're not sending messages back and forth, there is a certain amount of resource that is being tied. What else? Yeah. Actually, a lot of the kernels, they will say, okay, 1,000 sockets. Or 1,000 file descriptors, open files, basically. Or something like that. What else? What's the other problem? There could be security issues because this connection is open and maybe this application does not terminate properly. There could be. Yeah. Could be. What else? It's the same thing that we talk about when we do object-oriented programming. Right? Once you allocate a resource, you need to deallocate it when you no longer need it. Otherwise, the amount of memory, amount of resource that you're using is going to grow and grow and grow, and then at some point, everything's going to come crashing down, right? Because sockets are special files, we have applications running across the network. You do have to worry about, what happens if this connection request does not get through, right? For example, let's say you have two nodes that are talking to each other, and you just shut one of the nodes down. What do you do in that case? So there are some of the special cases that you need to worry about. The normal case is, you send messages and then you call, shut down or close. But there are some abnormal cases you have to worry about. You can basically also open UDP sockets if you want to. And finally, I'll just take one more minute. What we talked about until now is how do you have one application talk to one other application running across the internet, right? But a lot of times, let's say we're thinking about a web server. It's serving files to a lot of clients. You could sell at the same time. So you need to do something special for this to happen because you can't afford to just send all the response to this client, and then once you're done with that, send all of the response to this other client. You can't afford to do that because let's say one of the clients is on a really slow internet connection. What happens in that case? You're going to have all these outstanding requests piling up while you're sending this message to this client really slowly, right? So you need to do something called asynchronous I/O. And you're going to learn how to do this in homework 4, basically. How can you actually talk to a lot of network clients really fast, even though some of those clients might be running really slow. So that's called non-blocking I/O. All right, so just look at the slides, but more than the slides, I think the PDF is excellent here in this case. All right, thanks.
Yeah, he's gonna try to say 4 people.
You really?